Welcome back. We are now continuing with the chapter on solutions. In this part of the lecture, we are going to talk about the solubility of solids, because you can dissolve solids, you can dissolve liquids, and you can dissolve gases, right? So we're going to concentrate on dissolving solids, and we are going to see how we are going to relate that with temperature, and we are continuing basically focusing on aqueous solutions because we are using water, which is most of what we have on this planet. And I would like to begin by showing you this graphic. And what this graphic is showing us is the solubility of ionic solids as a matter of temperature, like I said. But let's break this down into concepts first. So solubility is the amount of mass that you can dissolve on certain amount of water. To make it standard, we tend to define solubility as the amount of mass that you can dissolve of the solute in 100 grams of water. Sometimes you're going to see the amount of mass of the solute in a given 100 milliliters of water, because remember, the density of water is 1 gram for every 1 milliliter. So you can interchange grams and milliliters at a standard condition, basically at room temperature. It's not exactly a 1-to-1, but we're going to say it's 1-to-1. And what's the other concept that we have to understand? Ionic, and you already know ionic. Ionic is a compound that is made out of a metal and a non-metal. And you remember how to find those on the periodic table. So all these are going to be ionic compounds: metals and nonmetals, metals and polyatomic, metals and nonmetals, and metals and nonmetals. So that's what we are discussing with this graph: the amount of mass that you can dissolve of an ionic compound given mass per every 100 milliliters of water, or 100 grams. And this is what we tend to observe. With the exception of cesium sulfate, with the exception of that one, all the others, as you increase the temperature, the amount of solid that you can dissolve increases, as the graphic shows for every one of them except cesium sulfate. And I once asked somebody who knows a lot more than me, physical chemist, how come this one doesn't follow this trend? And what they told me is, when you make the solid, the way the compound arranged on the lattice or on the network to make the solid, sometimes as you decrease the temperature, this particular one tends to become more organized, which makes it more cohesive and it cannot be separated. The other ones follow the logic. And what does the logic tell us? The logic tells us that if we have an ionic compound, and it's going to be a lattice, you never find just two. It's going to be like a network. And you've seen this pattern before, right? When you have a lattice, a solid, and in case that I'm not pronouncing that right, it's lattice. When you have a network of the ions like that, as you and they are all particles are always moving unless it's 0 Kelvin, so 0 degrees Kelvin. So at any other temperature, they're always moving. In the solids, they're not really moving, they're vibrating. So particles are always moving. If they're not actually moving, they are vibrating, and that's their movement. So as I increase the temperature, that vibration is going to increase. And if I used to have a positive neatly aligned with a negative, that vibration is probably going to cause them to start getting farther away from each other until the force that is keeping them together is no longer there, and then they can be taken by the solvent and forming the hydration cage that we talked about before. So as the temperature increases, it makes sense that they're gonna vibrate and they're gonna break apart from each other, so they're gonna dissolve. So as the temperature increases, more and more of it should dissolve. And that's how the temperature relates to the solubility of ionic solid, with few exceptions. And for those, we gotta go deeper. But in general, all ionic solids that dissolve in water will experience an increase in solubility as the temperature increases, because you are increasing the kinetic energy, therefore disrupting the forces that are keeping them together. So with that in mind, let's answer these three questions. First part, what are dissolved particles in a solution containing an ionic solute? I just showed you. If we have an ionic solute, we're going to have cations and anions. So the particles are going to be cations and anions, which are nothing more than ions, right? Which are charged particles. So that's what we have on a solution in which the solid was an ionic compound. And what is the name? What is the name of this solution? When you have a solution that is made out of ions, we're going to call that an electrolyte. So an electrolyte is going to be a solution that contains ions. And for those of you related with medicine, you know that electrolytes and sports and other things, you know that electrolytes are super important in our bodies, because they provide the ions that allow us to regulate the neurons firing, the muscles, the neurons helping the muscles open, the cell membrane opening and closing, allowing nutrients in and waste out. So electrolytes are super important. That's why if you become dehydrated and you end up going to the hospital, the first thing they do, they're going to give you an IV of electrolytes. And that's whenever you're doing a lot of exercise where you're sweating like crazy, you should be drinking electrolytes to keep those ions in your body at the level that they're supposed to be. So if a solution is not an electrolyte, we're going to call it then a non-electrolyte. For example, if I take sugar is made out of carbon, oxygen, and hydrogen. It doesn't contain any metals, so it's not an ionic compound. But sugar dissolves in water because a molecule of sugar separates from another molecule of sugar, but they do not create ions in the process. So that would be a solution that is a non-electrolyte. What about the next question? So the next question, a solution contains 28 grams of potassium nitrate in 100 grams of water. So 100 grams of water is probably talking about solubility, right? Because that's how we measure the solubility, in 100 grams of water. And it's at 25 degrees Celsius. We have temperature here. So 25 degrees Celsius is going to be, I guess, somewhere in there. Somewhere like that. Let me do that better. So that would be around 25, more or less. Is the solution unsaturated, saturated, or supersaturated? Unsaturated means that it has some solute dissolved on it, but you can still put some more in there because there's still some water molecules that are not busy forming the hydration cage. Saturated means that every molecule of the solvent, in this case water, is busy being part of a hydration cage. So if you put something else after that point, it's just going to go straight to the bottom. It's not gonna dissolve. And supersaturated is where you probably warm up the solvent and you were able to force more solute into the hydration cages. So it's kind of balancing there. And anything you do to it, it will throw the solid with force out into the out of the solution. So how do we know if 28 grams of potassium nitrate in 100 grams of water at 25 degrees Celsius is going to be unsaturated, saturated, or supersaturated? Where we're going to look at the graph and we're going to find potassium nitrate, which is going to be right there. So that's the curve for potassium nitrate. And according to this curve, at 25 degrees Celsius, 25 degrees Celsius, it's going to be around 38 grams of potassium nitrate that can be dissolved. So that's going to be an unsaturated solution because you can dissolve 38 grams of potassium nitrate in 100 grams of water. So 28 is less than that. So that means it hasn't reached the saturation point. Saturation point will be 38. That's the maximum. So this will be a unsaturated solution. So that will take care of that one. The next one is a potassium nitrate solution contains 45 grams of nitrate per 100 grams of water. So we're still talking about the solubility table. And it's cooled from 40 to 0 degrees Celsius. So what happens during the cooling? Well, the first thing we know is that during the cooling, the molecules are going to slow down, right? Because they're losing energy. They're cooling. They're losing energy. So the kinetic energy is diminishing. If they slow down, the intermolecular forces then can hold grab, and the partially positive can find the partially negative, or the positive can find the negative, and they begin to precipitate or form the solid. So if we start, so we're still doing potassium nitrate. If we start at 40 degrees Celsius, that will be right there. So 40 degrees Celsius will be that there, which means right here is where we will start, which is around 63. So at 40 degrees Celsius, I can dissolve, the water will become saturated at 63 degrees Celsius. So 63 degrees Celsius, I can dissolve up to 40 grams. 40 grams, let me fix that. 40 degrees Celsius, I can dissolve 63 grams. That's what I meant to say. I'm sorry. So what happens if I take it down to 0 degrees Celsius? When I make it to 0 degrees Celsius, I can only dissolve around 12 grams. So if I have a solution that contains 45 grams of KNO3 at 40 degrees Celsius, that will be an unsaturated solution because I can dissolve up to 63. So it's going to go from 40, I'm going to go down to 39 probably. At 35, let's see what happens at 35. At 35, now I can dissolve only about 50 something. So I got 45, so at 35, nothing happens, no change. At 30 degrees Celsius, it would be, at 30 degrees Celsius, it would be like around here, which is going to be around 45. Okay, so at 30 degrees Celsius, Anything after 30 degrees Celsius, I will begin to see precipitate. At 30 degrees Celsius, I can only, the maximum I can dissolve is about 45 grams. So anything below this, I will suddenly see precipitate forming. And when I make it to 0 degrees Celsius, I'm gonna see some solid at the bottom of the beaker or whatever flask I'm using. And based on the graph, at 0 degrees Celsius, 12, this should be exactly 33 grams, 33.5 grams. How do I know how much is going to be at the bottom? Well, at 0 degrees, the maximum I can dissolve is 12. Since I begin with 45, the difference is going to be the precipitate. So you should be able to do something like that, and that will tell me that you truly understand how the solubility of solids relates to temperature, in particular if you have a graph given to you. So with that in mind, you should be able to do that daily work. And once you do that daily work, you should be able to do that daily work. And once you do that daily work, you should be able to do that daily work. But let me do the first one. I want to show you how I will approach the first one. Determine whether each of the given amount of solid will completely dissolve in the given amount of water at the indicated temperature. We got 45 grams of calcium chloride. So we're looking at calcium chloride, which is going to be right there. We're talking 5 degrees Celsius. So we're talking around here somewhere. So we're referring to, so we basically are concerned with this point on the graph, which is going to be 60 grams. However, look at this here. This is different. The graph is based on 100 grams of water. This is 105. So how do I approach this problem? It's relatively simple, because this is telling me that at 5 degrees Celsius, I can dissolve 60 grams of CaCl2 for every 100 grams of water. That is straight from the graph, right? At 5 degrees Celsius, according to where it intersects the line, I can dissolve a maximum of 60. But that's 100 grams, which is nothing more than 0.6 proportion, right? So all I have to do is 45 grams at 105 grams of water and find out what that is. So what would be 45 on 105? Let me do the calculator. So the proportion between 45 to 105 is going to be 0.43. So at 5 degrees Celsius, I can dissolve often 0.6 proportional. What I have is 0.43 proportional. So yeah, that's less. So I should be able to dissolve that. So the maximum I can dissolve at 5 degrees Celsius is a proportion of 0.6. What I have at 105 grams is a proportion of 0.43. Another way to do this is you can say 60 grams for every 100 grams equals 105 grams to X, and then whatever X is, you're gonna compare that with 45 grams. So let's see what when we do it like that. So to find x, I'm going to multiply 60 times 105 divided by 100, and that's going to be 63. So, which means if I have a little bit more water, I can dissolve all the way to 63. I only have 45, so the answer would be yes. Having a temperature of 5 degrees Celsius and a total amount of water of 105, I can dissolve a maximum of 63. Since I only have 45, yes, it will completely dissolve. So that's how I would approach that. The other way we did it, we did the proportions. We said, well, the proportion is always 0.6 at 5 degrees Celsius. So my proportion is less. So yes, it should completely dissolve. So you can approach it either way. So the answer to this one is yes. So what about the other two? And please show your work. You know, I'm always looking for that, right? Because we're doing the daily work. So I gotta see the work. So once you finish that, I will say that you have a pretty good understanding of how temperature relates to the solubility of solids. What about the solubility of gases? How will temperature relate to the solubility of gases? Well, let's do that by looking at this poor fish. So somebody that was well-intentioned prepared a fish tank, and they said, well, if I boil the water, I will kill all the germs, and my fish will be on a super clean water. So they boil the water, and then they cool it. They're not dumb, so they're not going to boil the fish. So they wait until the water cool, but when they put the fish in there, the fish die. How come? And the way to explain this is by looking at this diagram. So what is a solution? A solution is a homogeneous mixture. Fish breathes oxygen just the same way you do. They do not take the water, break that, and breathe that oxygen. A lot of people, that's what they believe. That's not true. If not, the ocean would be gone by now, right? They just breathe the same oxygen you breathe. Where is that oxygen? That oxygen is in the air. And the air is touching the water. And the air is made out of particles, right? And the particles, according to the kinetic molecular theory of gases, they moving randomly. So when they happen to be moving into the water, they just made a solution. And they will continue moving, and every so often they come out. And that's what we get learn that we call vapor pressure, the movement of particles hitting back and forward. But when they hit and they go inside, now they're part of the solution. Now you have the water with something on it. So that's a mixture, that's a solution. So when this person boiled the water, they gave a lot of kinetic energy to the oxygen inside the water. So all these particles were able to escape because they were moving faster. And since they were moving faster, the probability that they were pointing up increased. And most of them went out, and the content of oxygen in the water diminished immensely. When the fish went in there, it took the first breath through its gills, and then there was no more oxygen, and the fish died. That's why on a lot of chemical manufacturing companies or any manufacturer that use water, when they use the water, sometimes the water, because of what they're doing, gets hot, and they dump it into the rivers. In the past, before we have the Water Act regulation, in the past, when they threw that water into the rivers got hot, and a lot of them lost their oxygen, and you usually saw a lot of fish dead on the shores. One of the things that companies have to do nowadays is that they have to wait until that water cools down before they put it into the river. And that's coming from using common sense and science. So gases, because the gas inside the solution is still moving, when they move fast, they can escape. So the solubility of gases, contrary to the solids, decreases with high temperature. The solids, the solubility increases. The gases, the solubility decreases because it escapes, it leaves the solution. However, one way to prevent that is by putting pressure, because if let's say I put a piston in here and I move it down, it's going to bring these molecules closer and closer to the water. They're going to be more concentrated now. They're going to collide more often with the water, and they're going to become part of the solution. So increasing the pressure forces the gas molecules to go inside the solution. So increasing the pressure increases solubility. Increasing the temperature decreases solubility. And any 3 years old can memorize that. The question is, can you, as a college student, explain why using the kinetic molecular theory of gases and what a solution is? So that's what we're going for, that understanding, not memorizing. If you're all memorizing, you're out of a job, because Google have that taken care for you. So with that in mind, you should be able to explain this by the knowledge you have about the kinetic molecular theory of gases, and by knowing that increasing the temperature decreases solubility, and by knowing that increasing the pressure increases solubility for gases. For solids, increasing the temperature increases solubility. And once you do that, we are done also with relating the temperature to the solubility of gases. So when we come back and we go into part C of this lecture, we will begin doing calculations, the part that you love, the math. So, and we will begin talking about mass percentage. So we're going to start defining, okay, you got this much solute into this much solvent. When you put them together, they made the solution. So can you tell me in numbers which one is more concentrated or not? And that's where we're going to go next time we meet. So until the next one, if you're watching this over the weekend, have a wonderful weekend. If not, have a wonderful day. See you later.